There are many forces that change with the position. For example, the elastic force of a spring is proportional to the distance stretched or compressed. The force of gravity on a spaceship that is leaving the Earth and is flying to Mars changes as the inverse of the square of the distance. If we want to calculate the work done when moving an object under these forces, we need to apply the definition of, we already know of work, but now, as in each position there's a different force, we need to integrate the work all through the path taken to move the object from its initial position to its final position. We can think this as assuming all the little portions of work done in every tiny interval. This inner limit is the following integral. Let's consider Hooke's law for a spring. Let's calculate the work done to stretch a spring from its initial position to any certain final elongation. The force is minus k times x. This is a one-dimensional motion which we integrate from x initial to x final. The integral is 1/2 of k times x squared, evaluated between the initial and final positions. Thinking back to the meaning of an integral as the area under the curve, we plot the force as a function of position. The area under the curve is that work done. Let us now consider the gravitational force of Earth near the surface of the Earth. If we don't go far from the surface, the force done by gravity is the weight m times g. Let's calculate the work done to lift a mug from the ground to a certain height. In this case, we follow the same steps as before. We're considering lifting it upwards in the y-axis. The integral from the ground, which we can consider our origin, to an arbitrary height y is. So this leaves us with work equals to the integral of mg times dy, but because the force is constant, it can go out of the integral. The integral is mgy.